All right. The next thing we have to talk about is our our valves. And so here is the basic symbol for a valve. Some of you may have seen that before. So we have it is what it is, and delta P is the pressure across the valve. Now there are many kinds of valves, and which will have many kinds of models, but one of the common models that we'll be working with is this one. This is the one your book is using, governing equation. And so the idea is for a given valve setting position, you have the following equation. So as you change the valve setting, you would be changing things, but the idea is that the valve is in a set position and that you have a model for it as such. And it's the flow rate equals this K, and K is would be a characteristic of the valve, so we'll put that on top, square root of the pressure drop across the valve. All right, so here's what the valve pressure flow curve would look like. So as you have the change in pressure, then you get, and so depending on where you are, then that would determine the flow rate you get. Okay. Now this would be a nonlinear thing to have in a differential equation. So we're going to linearize it. And so basically what we'll do is we'll say, well, there'll be some nominal pressure drop that we're working across with some nominal flow, and we will basically have perturbations around this point. And as you see, while this is nonlinear within a region, it'll work fairly well. So we're going to linearize this with, by looking at the slope, we'll call that 1 over r. And the idea is that we'll in the end be able to say r times omega equals the change in pressure. But we need a little more work before we get there. So we have nominal pressure drop, nominal flow rate, and we need an equation for the tangent, and that would, so we're looking at omega, where we actually are here, somewhere along here, the actual flow rate is equal to omega bar, the nominal rate, plus we're just moving along the slope here. So 1 over r delta p. So wherever we are, and we jump up to here, we have that slope, and then that would take us over. So that's how we're modeling this. So we have change in pressure, and we'll note that that change in pressure can be basically written as the base pressure plus, here's this, or the actual pressure minus the nominal pressure. So wherever we are, here's this minus the nominal pressure would give us this dynamic variable. Okay, and note we could bring this omega bar to the other side, and so we'll have omega minus omega bar, and we would have essentially, we could be doing this piece. Okay, so this is what we're setting up. So we need to figure out this, how we're going to model that, and we're going to do it using a Taylor series expansion. This is the most common way people will linearize things. So when you have something that's nonlinear, and you're going to go, basically you're going to set up an equation around these nominal points, okay? And so here we have, we're going to have omega equal omega bar plus d omega d delta p, okay? So that's the actual slope. So we're going to find the slope of that. And then from there, we would work with delta p minus the nominal, okay? So that's just what we're setting up here. So it's Taylor series expansion says we're just going to take this first derivative and we're going to ignore all the future ones. So this is what we're going after here to compute that. All right. So this will wind up being our first order approximation of that in the basis of our model. When we compute this would be 1 over the resistance, because at the end of the day, we want to have basically where we're heading, R omega hat equals delta P hat, and this is kind of like R times I equals voltage. So same gig. All right. So this is kind of what we all have here, so I actually don't need that. Take that out. So we need to compute R. Well, that's just, we know this relationship, and so we want to compute this derivative, W relative to delta P. And so we stick in for what W is, K delta P to the 1/2. Take the derivative and evaluate it at the nominal rate. So when we take the derivative, we wind up with 1/2 K, the delta P to the minus 1/2. And actually, this is not right. It is K delta P to the minus 1/2, but I had already put it in the bottom, so that was correct. All right. So now here, this is to be 1 over R, so we just bring R to the top, flip everything around, and we would have the following. 2 delta P to the 1/2, the nominal one, divided by K. So that's just turning those upside down. But I would note it, if I add a K in here and a K in the bottom here, that's just adding a factor of 1. That makes that K squared, but now this is K, the square root of delta P. And that's just this equation, which then is the nominal omega. And so we have R equals 2 omega on K squared. So here's the good news. When we have problems, K, this K will be given. This is a valve constant. It's valve would be given with the valve. So all you have to know is the nominal flow, the value of K, and you can come up with R directly. So you can skip all of this, but this explains how we handle nonlinearities. If you go on to more sophisticated courses in systems, you will spend much more time dealing with nonlinearity. So we're just more focused today and in this course on exposing you to them and kind of letting you see the process. But as you move on, this is something that you may need to get into with more depth. So this is how we handle valves. They look like this. Knowing omega, knowing K, boom, you have R. And so the linear model is just what you would expect based on resistors, and these are an analogy. All right, I'll see you next time. Bye now.